I didn't turn the camera on when I gave the first explanation of this problem. So this camera is now on. The other camera has a good video. This will be a better one, and it'll be shorter. Okay, so we want to talk about multiple scaling. You'll understand by the time we get to the end of this what I mean by multiple scaling. We're going to assume that we've observed frequency versus length for pendulums in the lab, say for pendulums up to 2-3 meters long. And we've got our frequency versus length graph. Okay, so we're going to assume that having done that, we obtain a Y factor of about 0.63. We've done this carefully, and we think that we've done it to two significant figures. Now, I don't guarantee that a Y factor of 0.63 gives you a power P that's pretty close to -2/3. I know it's pretty close to -2/3. How close I won't guarantee right now. It's within a few hundredths. So that our frequency versus length model is frequency equals A times L to the -2/3. Now, the units of A, of course, are going to be determined by the units in which you've observed L and F. If you observe L in meters and F in cycles per minute, you're going to get a different value of A than if you measure L in, say, inches and frequency in cycles per second. Okay, that should be obvious. Okay, well, in any case, now let's assume that we've taken some data to corroborate our results with much longer pendulums. We go out and find a tower 100 yards high, build a 100-yard pendulum. We go out and find a tower high enough to build a 1/10 of a mile pendulum. There are such towers. I doubt that we'd get access to them, but we could always try. And we observe the frequency of the 100-yard pendulum to be 3.2 cycles per minute, and the frequency of the 1/10 of a mile pendulum to be 2.3 cycles per minute. Now, in reality, if I went to the trouble of doing all this, I would observe the pendulum for at least a good hour, maybe a good day, although I wouldn't be the one doing the counting manually. We'd do it electronically somehow. And I'd be able to get the frequency to more precision, maybe three significant figures, 3.286 and 2.319. Wind, air movement, and so forth, also the rotation of the Earth, can have an effect and limits the number of significant figures we could actually get. So really, in reality, with air resistance and other factors, I think we'd have trouble controlling this to get much better than three significant figures on each of these results. Anyhow, that's an aside. Okay, so we have this. Now, what am I asking you to do? I'm asking you to use the same scale for the frequency. Now, the scale, I've already labeled it, is in cycles per minute for both of these, so it's sensible to use the same scale for frequency. Want to label the graph according to the first data point. Now, that's circled in yellow, this is in yellow, so this is what I mean by the first data point. And this first data point indicates frequency 3.2 cycles per second, length 100 yards. So how would we label the graph? Well, let's find 3.2 cycles per second here on this axis, mark a point, and there's our 100 yards. That's pretty straightforward. Or we could mark the point first and then project over here to get our 3.2 cycles per minute and project down to get our 100 yards. Okay, so what I want you to do then, I want you to now label the graph again according to the second data point. Now we're going to use the same curve, but of course our length is measured in different units. So we're going to have a different labeling for our length. So maybe we complete our labeling for the yellow data point, the first data point, 100 yards here, 200, 300, 50, 150, 250 yards. And then we do labeling for the second data point. And I'm not going to tell you how to do that. I'll do a subsequent video with hints, and we'll look at how that might be done. But for right now, just going to give you the instructions, okay? So that's going to give us a dual labeling of the L-axis. Now we can use that dual labeling, turns out, to figure out how many yards there are in a mile. Now we already know how many yards there are in a mile, although people really don't know how many feet there are in a mile or how many yards in a mile anymore. But it's easily accessible information, and if you had to use it, you'd be able to quickly learn what those numbers are, and maybe you do know what those numbers are. So, we use the dual labeling to determine how many yards in a mile. I'm not going to tell you how to do that. Look at the graph, use your knowledge base, use your insights, use your intelligence, and don't feel too badly if you get a little confused here. I would give this a day before I would start looking at hints. Okay, so now the dual labeling might give you inconsistent results. As a matter of fact, it's impossible that the results would be completely consistent. But the question then is, how inconsistent would they be? So you want to think about the consistency of the dual labeling. And I'm going to leave it to you to think about what I mean by consistency. Again, if you use your insight and look at the dual labeling, you'll see that there are some contradictions if you try to use the dual labeling to determine how many yards there are in a mile. I'll give you one hint that different parts of the graph are probably going to give you different parts of the L-axis are probably going to give you different results. So you want to think through that, and then, and this is very challenging, speculate on why it might be so. Okay, in terms of what we actually do with a pendulum, why might it have turned out this way? And you know, the reason is that maybe we screwed up our count or something, but let's assume we didn't. So what could be the source of whatever inconsistency we see? Something you always want to think about when you're applying math to anything that happens in reality.